actually get generalized. Okay, so now let's talk about these faces. So let's say there is a simplex is a R simplex given by sigma R, and let's take a very simple choice. Let's say P0 P1 da 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 P of R. This is R, yeah. Then for any Q which is equal or less than an R, a Q face, so to say Q dimensional face of this sigma R is given by sigma of Q, which is sigma of Q equals to P0 P1 dot 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 up to P of Q. So it's like let's take an example to understand what this really means. Okay, again I'm gonna take a three-dimensional example of this polyhedron. So this is P0 1 2 3 4. So let's call this polyhedron as, let's say, sigma 4. It is denoted by sorry, not sigma 4, this is 3 simplex, yeah. So this is P0, oh, sorry, not, yeah, 0 1 2 3 4. Okay, now this is our polyhedron, and now we want to see some faces, a Q face. Let's say the value of Q is now what? Let's say 4. Okay, so what do I mean by Q equals to 4? So let's say Q is equals to 4. What do I mean by that? Well, it means that I have to build another simplex that only contains 4 zero simplices, right? So that, if I do that, let's say Q equals to 4, then that would be, let's say, this P1 P4 P3 P2, P1 P4 P3 P2. Okay, that's the face. So similarly, you can even go beyond. Let's say you can type Q equals to 3. So you are taking a 3 face. So this will be a 3 face. This P0 P1 P4. This will be a 3 face, and so on. Okay, and it's a very interesting idea that when you put Q equals to 2, you have this P0 P1, let's say, that line is also a face, but it's a 2 face. And then the points itself, this P0 P1 P2 P3, these are 1 faces. Okay, because it only contains a P0 P1 P2, that means it only contains a point. So if I summary that up, when I say Q equals to 4, this means I'm talking about a face that is P1 P4 P3 P2. When Q equals to 3, I have this face, that face, and this one, 3. Even though the drawing is not very good, you can understand that I can actually take these combinations of P0, 4, 1, and 3, right? So there should be 1, 2, 3, 4. 4 3 faces. So there will be 4 3 faces, and let me just write down one for your convenience. Let's say this is P0, P1, and what was the other point? It was P4. P4 and 3 others. Similarly, when you say q equals to 2, you are talking about lines which are called, so this is a 4 face. Again, this is a 4 face. We call it this a 3 face of this tetrahedron. We call this 2 face. When q equals to 1, this is just all the points that we have. These are 1 faces. So you may ask, okay, we did draw the polyhedron, but if I have more than 4 points, or let's say I have a 4 simplex that contains or a 5 simplex or higher dimensional simplexes, how can we write down these faces? The idea is very simple. We have this initial set, right? Or so to say, the set of points, this one, P0, 1, 2, 3, 4. From there, it's just actually a combinatorics problem to find out the faces. So let's say we have something like this, P0, P1, P2. I'm taking the smaller example. So if I want to find out, find out all the faces, I'll do the following. And by all the faces, I mean the 0 faces, 1 faces, 2 faces, and so on. Do the following. So at first we have these 3 points, P0, P1, and P2. So let's say I'm calling this F for now. I want to assign these faces to a set. So the first one is P0, then I have P1, then I have P2, right? So these are all the 1 faces. Now I want to talk about 2 faces. I want to see how many 2 faces are there. So I can take P0 with P1, right? Then I can take P1 with P2, right? And I can also take P2 with P1. These are my 2 faces. And if I want to talk about a 3 face, then I have to take all these 3 points, which is just the simplex itself, P0, P1, P2, right? So 3 face. So from here you can easily see that these 3 points will actually give me a triangle like this, P0, P1, P2. And these 2 faces are just these lines, these 1 faces are these points, and this 3 face is the field of area over here. Okay, the simplex itself. And these 1 faces and 2 faces will be called proper faces of this simplex. So whenever we have faces, that means the value of q is less than, strictly less than, it cannot be equal to the value of the r simplex as q equals to r. So whenever this q is less than r, we call them proper faces. Okay, and it can be equal to q can be equal to r, but in that case we don't call it a proper face. So let me write that down. So let's say we have a r simplex, then let's also say we have a q face of this simplex such that q is less than r. It's not equal to r, it's always less than r. Then that q face is called a proper face. face of that simplex. It's just a terminology that, like, let's say you have a triangle, right? So the triangle itself is a simplex, and then there is this face, the field of region in between. This is what would you call intuitively a face. So we are just calling this type of faces as proper faces. Okay. And yeah, so this is our discussion about faces, and from this example and the previous one, we can also say that for any n simplex, the number of m faces is given by the combinatorial thing that you see, plus 1 combination with m plus 1. Okay. Now that we have talked about a while for the simplexes, now we want to move to the thing that we wanted to talk about earlier. That is, since we talked about the simplexes, we now want to move to simplicial complexes. So let us do that.